Section 5.2, Infinite Series. This is from OpenStax Calculus Volume 2. At the bottom of every page there's a link. Please follow that to download the textbook. It is an amazing textbook, and this is meant to supplement that book, so they go very, very well together. So, infinite series. While a sequence is an infinite list of items, or of terms here, okay, when these are added together we get what we call a series. This is an infinite sum. So a series is a sum of infinitely many terms of the form, the sum from 1 to infinity of a sub n is a sub 1, a sub 2, a sub 3, and we are summing these, and continuing until never. We continue. Okay, so the question really is, how do we find the value of an infinite number of things? Well, we could start by adding the first one, and the second one, and the third one, and the fourth one. We can add a whole bunch of them, but that really doesn't give us the whole picture. So what we do is we consider the partial sums. Okay, the partial sum is the sum from 1 to k of a sub n. We consider this, so we're going to take the sum of the first one, then the sum of the first and the second, then the sum of the first and the second and the third one, the first through the fourth, the first through the fifth, etc. Okay, now this forms a sequence, and we call it this. The partial sums form this sequence of partial sums. If it converges, then that means that the series converges to some value at the end. And we can then write the sum from 1 to infinity of a sub n equals s, where s is the sum of that series. And it's the limit of that sequence of partial sums. If the sequence of partial sums diverges, then we say the series diverges. Now, a very useful tactic here. It is often helpful to compare the sequence of partial sums, to some other sequence. It's useful to compare that to another sequence that obviously diverges or obviously converges. Okay, so let's go ahead and look at the sequence of partial sums for this series. The sum from 1 to infinity of 1/2 to the n minus 1. Now we've dealt with the 1/2 to the n minus 1, that sequence, but now we are summing those terms. So S1, our first partial sum, is just the sum of the first one item. So 1. S2 is the sum of the first two, which is 1.5. I'm going to make some approximate values here. S3 is 1/2, 1 plus 1/2 plus 1/3, which is exactly 1/4. Haha, makes a huge difference. All right, so that is 1.75. S4, 1 plus 1/2 plus 1/3. What am I doing? 1/4 plus 1/8, which will be 1.875. So we're going up in powers of 2. So 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and that is going to be 1.9375. So it appears that this sequence of partial sums, Sk, is approaching, these values here are approaching 2. It appears that is the case, and it is. And we'll see later with geometric series, this is a geometric series. Okay, so it appears the sequence is approaching the value, so we can state that the infinite sum there is 2. Alright, let's look at another example. Determine whether the series converges. The sum from 1 to infinity of n over n plus 1. Okay, so let's first consider what this sequence is. The first term of this sequence is 1/2. The second term is 2/3. The third is 3/4. 4/5. 5/6. And we have something that looks like that. Those are our terms. So our S1 is 1/2. S2 is 1/2 plus 2/3, okay, which I'll go ahead and say is approximately. That's approximately 1.16. S3, that would be 1/2 plus 2/3 plus 3/4. That is approximately 1.916. 1.916. S4, so that would be 1/2 plus 2/3 plus 3/4 plus 4/5. That is approximately 2.716. Okay. Now, it appears these numbers are increasing. Okay. I don't see any signs of slowing down or stopping, whereas the previous problem, they were getting very close, 1.937. They're getting much closer as we go to 2. Here, it doesn't really appear that they are going anywhere. So, here is the observation we want to make. S1, actually, let's go with this. S2 is greater than 2 times 1/2. It's a little bit bigger than 1. S3 is greater than 3 times 1/2. S4 is greater than 4 times 1/2. And in general, the partial sum Sk is greater than k times 1/2. It's greater than that. So what that means is that since this sequence here is going to infinity, it diverges, then Sk must also. Okay, so Sk goes to infinity, and the series diverges. Again, compare it to something that is useful if it doesn't appear to converge. All right, let's look at number 15. Determine whether this series converges. -1 to the n. So first, the sequence would be -1, 1, -1, 1, -1, 1, and it continues in that same pattern. So our first sum is -1. Our second sum is going to be 0. Third sum is going to be -1 plus 1 plus -1, so -1. S4 equals 0, etc. Okay, so this appears to just bounce back and forth. Okay, so the sequence of partial sums is -1, 0, -1, 0, -1. Now, this does not diverge to infinity, but it does alternate. Okay, so this diverges. The series diverges. Okay. Let's look at another. All right. We have the series n equals 1 to infinity of 1 over n times n plus 1. Okay, so let's make our terms first. So the first is 1 over 2. Second term, n equals 2. This would be 2 times 3, so that's 1/6. Our third term would be 3 times 4, so that is 1/12. 4, n equals 4, so that is 1 over 20. Okay, that's enough for the moment. So S1 is 1/2. S2 is 1/2 plus 1/6, which is 2/3. S3, 1/2 plus 1/6 plus 1/12. That is 3/4. S4 is 1/2 plus 1/6 plus 1/12 plus 1/20, and that is 4/5. So it appears Sk is going to be of the form n over n plus 1. Now this converges to 1. So since the sequence of partial sums equals or converges to 1, we will say the sum of n from 1 to infinity of 1 over n times n plus 1 equals 1. And this sequence converges to 1. Okay. Let's determine whether this series converges. All right, well, that series, first I'm going to rewrite this. This is 1 plus 1 over n. Alright, so S1, well, our terms, our first term is 1.5. Our second term is 1.5. Hold on a second. Oh, actually the first term is 2. The second term is 2 plus 1.5. So 2. Plug in the value of 2. That's 1.5. So this is a total of 3.5. Okay, we do 2 plus, or 3.5 plus 4/3. That's going to be about 4.83. Okay. Alright, so, and I just did, that was actually the sum that I just did. So let's write that differently. S1, S2, S3. So our terms are 2 plus 1.5, which is 3.5. 2 plus 1.5 plus, plugging in a 3, we get 4/3, so 1.3, repeating, which is 4.83. Okay, so I actually just did too much work. That'll be a better way to organize that. Okay, so let's see if we can compare. These don't appear they're going to have any sign of stopping either. The first one is greater than 1. The second term is greater than 2. The third one is greater than 3. So why don't we say that SK is greater than K? Now, as K goes to infinity, that puts SK diverging to infinity, which means that our sum is 1 to infinity of n plus 1 over n diverges. All right, the number 18, the next one we have here is very similar. It's very similar. So let's first rewrite this. I'm going to go ahead and rewrite that. N equals 1 to infinity, and that is going to be n plus 1 over n. Alright, so number 17 is a good one to compare to because that one we had SK was greater than K. If you notice, n is going to be at some point much bigger than 1. So we're going to have something very similar. So our sequence of partial sums is going to be greater than K, more than likely. Alright, so our terms, we have 1 is 2. Plugging in a 2, we get 2.5. Plugging in a 3, we get 3 1/3. Plugging in 4, we get 4 1/4. Okay, so the sequence is going to infinity. The sequence is increasing. So our sums are going to be S1 equals 2. S2 equals 4.5. S3 is going to be 7.8 repeating, or 7.83 actually, approximately. S4 is going to be 11, just over that, so just over 12. So the idea here is that this is bigger than 1, this is definitely bigger than 2, this is definitely bigger than 3. So SK is greater than K, and therefore our sum. Okay, so look back on that, on number 17. N squared plus 1 over n diverges. We cannot say it equals anything. So that diverges because as k goes to infinity, sk goes to infinity. Okay, now we're going to turn our attention to a very special series, okay, the harmonic series. Determine whether this converges. Alright, so let's first make out our terms. This is our sequence here is 1, 1/2, 1/3, 1/4, 1/5, 1/6. The one that I was accidentally writing earlier. Alright, so our sums, S1 is 1, S2 equals 1.5, S3 is approximately 1.83 repeating. Okay, so again, that's the S1 is 1, S2 is 1 plus 1/2, S3 is 1 plus 1/2 plus 1/3. S4 is 1 plus a half plus a third plus a fourth, which is 2.083 repeating. And we just continue in that way. Now, this doesn't seem to be stopping. You might wonder, is it going to approach something? And the farther that we go, this is like I said, it's a very special one, because the farther we go, it actually continues to increase. Okay, this one is particular because it diverges slowly. It diverges so slowly that even after 100 terms, the sum is still fairly small. Let's see, at 15 terms, it's 1.999939. At 20 terms, it's 1.99998. Oh, no, sorry, that's the wrong one. I was looking at the wrong chart. It is... Anyways, it gets bigger and bigger, but it goes very, very slowly. There we go. Okay, there's what I was looking at. 100 terms, it's 5, roughly. At 1,000,000 terms, it is only at 14 and a half. So it increases, but it increases steadily and very, very slowly. All right, so the way we want to make note of this is actually to look, we want to compare. So S2 is greater than, I didn't write that in there, 1 plus 1/2. Now, it's greater than or equal to at that point. S4 is greater than 1 plus 2 times 1/2, which is 2. Okay, S8 is greater than 1 plus 3 times 1/2. S16 is greater than 1 plus 4 times 1/2. Right, so the generic way to write this is S to the 2k, so 2 to the third power, okay, would be equal to, or greater than, actually in this case, is definitely greater than 1 plus k times 1/2. Now, fairly obviously, this is going to infinity, which tells us that the harmonic series 1 over n diverges. Okay, 2 more examples till we are finished with this. Evaluate the series. Okay, now this is going to use some properties that we have yet to speak of, but they're algebraic properties. So first, the sum, if both of these converge, if each of these terms converge separately, then we can just add them and compute them separately. So this is equal to, I'm going to factor out a 3, and that is 1 over n times n plus 1, plus, I'm going to factor out a 2 to make this look closer to something we have looked at before. Now, we saw previously, and you might want to convince yourself of this fact right here, that I can factor out a 2 there. It has to do with the exponent there. Right, now, we've already shown that this first sequence, this one right here, this sequence of partial sums, converges to 1. So that is 3 times 1 plus 2 times, we've shown that this sequence converges to 2. And since they all converge, we can do this, and that is a total of 7. Okay. We're going to apply those same properties to this series. Factor a 5 out. By the way, the integral is an infinite sum. We could use these same properties, factoring things out of an integral just like we can taking them out of this infinite sum. Alright, now this is 1/2 to the n minus 1. Now, 1/2 to the n minus 1, the sum from 1 to infinity of that is just 2. So this is 10. So if we do see a familiar series that we know converges, that is certainly helpful as you're evaluating these. All right, let's look at 22. Geometric series. Okay, a geometric series is something of the form a times r to the n minus 1. Now, if the value of r, if this ratio here, if that is less than 1, then it converges. And in fact, the sum is this. This is a very important fact. Okay, if the value of r, the ratio, is greater than or equal to 1, the series diverges. All right, so first let's look at this one right here. The absolute value of our ratio, -2/5, is definitely less than 1. So this is going to be equal to a, that is the first term here, so that is 1, divided by 1 minus r, -2/5. So that will be 7/5, so this sums to 5/7. Keep a lookout for a geometric series. Okay, evaluate the sum of e to the 2n. All right, well, in this case, we have a value of 1. That's our first term. If we plug a 1 in there, actually, if we plug in 1 there, it will not be that. That is deceptive. That is not necessarily our first term. If we plug a 1 in there, we have e squared. So our first term is e squared. Our ratio is also e squared. Okay, we can write this n equals 1 to infinity, and we could write this as e squared times e squared to the n minus 1. All right, well, the absolute value of e squared is greater than or equal to 1, which means that this diverges. Okay. Series diverges. Okay, number 24. We're going to consider this series just a bit. The 1 over n times n plus 1. If we use partial fraction decomposition, then we see that this is equal to this series. So let's write out this first partial sums. So S1 is 1 over 1, okay, 1 minus 1/2. S2 is 1 minus 1/2 plus 1/2 minus 1/3. S3, 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, which, if you notice, that's written below. That's in general, we have a bunch of canceling terms. The 1/2s cancel out here, the 1/2s and the 1/3s. All we're left with is the first and the last term of our sequence. So in general, it is 1 minus 1 over k plus 1. All the middle terms cancel out, and so this obviously converges to 1. This has a special name, and it's called a telescoping series, okay, where we have middle terms cancel out repeatedly. Okay. A telescoping series is a series in which most of the terms cancel out in each of the partial sums, leaving only some of the first and some of the last terms. Now, in the ones we're going to look at, most of the time the first and the last terms are the only two that are left. So in general, if it can be written in this form, bn minus bn plus 1, the sequence of partial sums is sk, and it equals b1 minus bk plus 1. If the sequence bk plus 1 converges to b, then the series converges to b1 minus b. So let's write these out and determine our sequence of partial sums. That way we can take the limit there. Determine whether the telescoping series cosine of 1 over n minus cosine of 1 over n plus 1 converges or diverges. Alright, well, sk in this case, if you notice, if you want to write a few terms out, you can see the middle terms do end up canceling with this. And so sk is cosine of 1 minus cosine of 1 over k plus 1. The limit, sk, it approaches cosine of 1 and this goes to 0, which is minus 1. So because our sequence of partial sums converges to cosine 1 minus 1, the sum of cosine 1 over n minus cosine of 1 over n plus 1 equals cosine of 1 minus 1. Okay, so it all depends on that limit of the partial sums. So if you recognize that it's telescoping, we can go ahead and write the sequence of partial sums. This one is also telescoping. We're going to have terms cancel out. So this is 1 minus e to the 1 over k plus 1. Now, as k goes to infinity, this exponent goes to 0, which means this approaches, that means sk approaches, oh, that should be an e right there. If you plug in a 1, okay, e to the 1. So this approaches e minus 1, which means that our sum 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1 equals e minus 1. Alright, and that is the end of this section. Of course, visit that website there to see more of this textbook, this great textbook, and that should be it.